just started, so it's not a big thing. So when you're talking about branches, we have got conditional branches, unconditional branches, and then these two things are required for. So if you are talking about a branch over here, which needs to go to label, first of all, we don't know in this particular stage, that's a decode stage where the branch is decoded, what should be the outcome of that condition. So for example, even though we have got a simple branch like a branch not equal, so what a branch not equal kind of branch is going to do, it has got two registers, and then it has got some immediate value, right? So this is actually what's going to happen. So in a branch not equal, you need to check the contents of these two registers, R1 and R2. Now if they are not equal, then you are going to jump. So because the branch says that branch if not equal, right? So if for example R1 has got a value 5 and R2 has got the value 10, then you have to jump because they are not equal. So if they are equal, then you are not going to jump, but if they are not equal, then you are going to jump. And where are you going to jump then? So in simple processors or RISC-based processors, you don't have much addressing modes. So for branches, you have a very common addressing mode, which is called a PC relative jump. So all of these jumps are relative to the program counter's position. So the program counter is pointing at this place. So every jump is relative to the current location of the branch. So what we do is we add this immediate value to the current program counter's value. So this immediate value has to be added to the current program counter value. So the program counter at this point, whatever the program counter value is, and then we calculate some address and we go over there, and that is our branch target address. So this thing is the BTA or the branch target address that we have to calculate, right? So for branch target address, what we need is the program counter value and the immediate value. So immediate value is part of the instruction, and program counter value can be determined in the first cycle as well as in the decode stage as well. So all of these things can happen over here, but it's not normally happening over here. So what we do is we calculate this branch target address also in the execution stage, and the condition also in the execution stage. In a normal branch, in the 5-stage pipeline that we have discussed, both the branch target address and the condition for the evaluation of branches is done in the execution stage. So both of these things are done in the execution stage. So in the decode stage, if the branch is currently in the decode stage, one more instruction has to come over here. So my question is, which of these instructions should come? The next one is the very next sequential instruction, but we don't know whether we have to go to that instruction or not. And then we have another instruction at a distance from this point, which is going to be executed if this branch is a taken branch, right? So we call a branch as a taken branch if it's going to jump, and we call that as a not taken or an untaken branch if it's not going to jump. So if it's a taken branch, then it has to jump, and then you should execute this particular instruction from the right cycle. But the problem is that for branches, it's quite early to determine which should be the next instruction. So what the branches can do in an easier way is fetch the next instruction, which they were doing, which the pipeline was doing earlier as well. It was always fetching the very next instruction and then move ahead. So it's going to bring some instruction into the pipeline. We don't know whether we have to execute that instruction, and then we are going to move ahead. So I'm going to come back to my slides over here now. So if I go through this particular picture, then it would be a little clear now. So what happens is, we were talking about this cycle when the branch was in the decode stage, a new instruction has to come, right? But then still we don't know what is the output of the branch condition. So we move on to the third cycle, where the branch is going to now evaluate the condition and also determine the branch target address, right? But at this point in the third cycle, another instruction has to come into the pipeline, right? So we have now got two different instructions in the pipeline, and the branch is also going to evaluate the condition, the target address at this point. Then what will happen is we are now going to, at the end of third cycle, we now have the data that branch should jump or should not jump. So let's say this branch was a taken branch. Okay, so if it was a taken branch, then these two instructions were wrongly started by the pipeline, because the branch is going to jump to some other location in the code, and these two instructions should now be removed from the pipeline. So if you're going to remove these, then this means, and you're going to start a new instruction from the fourth cycle, the correct instruction from the fourth cycle. So this means you have lost two cycles. So the correct instruction should actually start from the second cycle, because that was its right place. But because you don't know what the next instruction is, you continued on with the sequential instructions. And then later on, when you finally found out that this is not the right instruction, you have to remove that from the pipeline and then fetch the right one. And when you're going to fetch the right one, you're going to see that you have lost two cycles. So that is actually the control hazard. That is what is preventing the right instruction from starting from the right point, because you don't know what the next instruction is, right? So that is actually the control hazard, or the third hazard that we have. So if a structural hazard, we were concerned about hardware issues, a hardware preventing the next instruction from executing from the right side, from the right cycle. For data, the data was the issue. For control hazard, we don't know what the next instruction is, right? So that is because of the branches in the code. Now, how can we reduce this? How can we actually reduce this? These stalls. If we need, if we actually have two instructions in our pipeline, so how can we actually reduce them to say lesser number of cycles? So currently what we are seeing is we have got two cycles of stalls, and this is because we are determining the branch target address in the third cycle and the branch condition also in the third cycle. Now, had we performed the branch target address computation and the condition evaluation in the second cycle, then only one instruction would have been in the pipeline. And if possible, if we had done all these two things in the first cycle, then by the end of first cycle, we would exactly know which should be at the right instruction, and then you are going to see there won't be any stall. But the problem is, can you do this? Can you determine the branch target address and the the branch condition evaluation earlier in time? So that's the question. So I'm going to come back to Jamboard here. So right, so our problem is that the branches are evaluating the BTA and the condition both in the execution stage, right? And when they are doing this in the execution stage, two more instructions are in the pipeline, and if that branch is taken, then these two instructions have to be removed, and this means you are going to incur a loss of two stalls. Two additional cycles are going to be inserted. So that's that's even more than the load use hazard, because in a load use hazard we had just a single cycle stall, but here we are going to see we are going to incur two cycle stalls if the branch is a taken branch. Now this can be resolved, and instead of two cycles, we can have just a single cycle stall if we do these two things earlier in time. So what we can do is we can save one cycle from every branch instruction, for every taken branch instruction, if what we do is we calculate these two things earlier in time. So the question is, can we do that earlier in time, right? So when you're talking about branches, what happened is that these branches, for a branch target address, what you need is the program counter value and the immediate value. So because you need to add them to calculate this branch target address. So the program counter value would be available in the first cycle, because The program counter is the main thing from which you have fetched the branch instruction. So you have this value in the first cycle even, but you don't have this immediate value in the first cycle because that is going to come from the instruction. So you're going to fetch the instruction, take the 16-bit, the last 16-bit of that instruction, and that would be the immediate value. So if you're going to calculate the BTA without elongating any operation, then this means that this immediate value is available only after fetching the instruction. So this means you cannot find the BTA in the fetch cycle, in the fetch stage, but you can do that in the next stage, which is the decode stage. So instead of execution, what we can do is we can do this operation in the decode stage. Okay. So how is that done? So what I'm talking about is that instead of doing the operation over here in the third cycle, the branch can do a branch can calculate the target address in the second cycle, provided we have the right adder which was calculating the branch target address in the execution stage. What we can do is move that adder from the execution stage into the decode stage. Now, if we calculate the branch target address earlier, this would mean that it's going to help all the unconditional branches, because for unconditional branches we just need the branch target address, and if we have the branch target address, we would know where to jump, and only one instruction would be in the pipeline that we have to remove. So the loss that we are going to incur is just going to be one cycle, right? Now, if this was about branch target address, so this can be resolved because we see that this thing can be done because this value is available in the fetch stage, but this value is available in the decode stage. So this means that the whole operation can occur in the decode stage. But what about condition evaluation? So a condition evaluation needs the register contents, and we read the register contents in the decode stage. So for condition evaluation, we need the register contents, and there are always going to be some simple operations between registers. So let's say we have an operation between R1 and R2. That could be a comparison operation, a simple comparison operation, or sign checking operation, whatever. But we have to do some operations between registers. Now, when do we have the value of registers available to us? So the register contents are read in the decode stage. This means that if you want to do any operations on register, that register is available in the execution stage, not before that. Okay, because you need to read the contents, and the contents are going to be stored in the pipeline, and then in the next stage, which is the execution stage, then you can perform the operation. So this means that the condition evaluation is going to be a little difficult to convert it to be done in the decode stage. Now, what we can do is I'm going to just draw out the decode stage. So let's say this is a register file which is going to provide us with two different contents, R1 and R2, and these contents are going to be stored in a pipeline register, which is the IDEX pipeline register, because this stage is the decode stage and this stage is the execution stage. So this is a normal procedure that the two register contents are going to the pipeline register IDEX, and in the next stage we have an ALU over here which is then going to use these registers, and then it's going to generate a signal whether they both are equal or not. Now, if we consider what are the different conditions in the branches, we see here that in MIPS the branches are quite simple. So they are just simple comparison operation. For that, using a whole ALU to do those things are, so you can say it's misuse of resources, because ALU is a powerful circuit. It can do very complicated tasks. Comparison is one of them, but comparison can be done separately as well. So what I'm going to do is we are going to modify our diagram a little bit. So what we can do is, instead of doing these things through ALU, what if we have a comparator over here and we pass on the values that we have read, that we are going to also store it in that register to that comparator, and that the comparator is going to give us a signal whether the two are equal or not, right? Now if you do this, this will mean that you are going to do that at the end of the cycle, right? Because in a decode stage, what happens is we normally do the reading in the second half. So we are still going to do the reading operation in the second half. So we are talking about half of the cycle. So in the half of the cycle, there would be some kind of a reading operation done, and then what we are doing is another operation in the same cycle. We are also comparing the result. So the worst delay or the critical path would be going through the comparator. So I'm sure you know about the critical path. So the critical path is the longest path of any circuit, which is going to determine the delay. So now we have added one more operation in that pipeline. So if now we are assuming if the register read operation plus the comparator delay is less than half the cycle, it's less than your cycle time, half of the cycle time. So if I say TC is my cycle time, so TC by 2. Now if this is less than the cycle time, this means this operation is not affecting the cycle time. For the other half, what we are doing is writing to a register file, and for the second half we do the reading operation, and after reading we have a comparator. So if both of these operations, reading plus comparison, is not going to exceed half the cycle time, then this means that you are not affecting the overall pipeline cycle time, and you have included the comparator within the decode state. Now if this is the case, then instead of doing these two comparison in the execution stage, what we have done is we have also evaluated the condition in the decode stage. Now doing that in the decode stage means that instead of doing these two operations in the execution stage, we have moved that earlier in time, earlier in the pipeline. And this is going to be helpful for us, because now instead of doing these two things in the third cycle, we will be doing that in the second cycle. And so we are going to save one more cycle, because by the end of the second cycle we will have our BTA available, and we will also have our condition evaluated to know whether we are going to jump or not jump. So if it's a taken branch, then it's going to jump to the right instruction from the start of the third cycle. So instead of starting it from the fourth cycle, it's going to start from the end of fourth cycle and at the start of third cycle. And this would mean that instead of 2 cycle delay, now we have reduced that to 1 cycle stall, right? So I'm sure if it's okay for all of you, then if there are any questions here, then I can answer that. Then otherwise, I'm going to take a break now, a small break for the Maghrib prayers, and then we are going to join after 10 minutes. Is this thing clear? So then I'm going to come to the other topics of control hazard. So is the control hazard clear? So we discussed about the control hazard. We discussed also how to reduce the the delays, the penalties from 2 to 1, right? So that can be done if the decoding part is done, if the branch target address and the condition evaluation is done earlier, which means that we do it in the decode stage, because obviously we cannot do it in the fetch stage. So instead of execution stage, we convert everything into decode stage. Now this will going to create more problems, some other problems that we are going to discuss after the break. But for the time being, what we have done is reduce the stalls from 2 cycles to 1 cycle. Is this thing clear? Okay, right. So let's take a break, and we are going to join at and at 7:10 or 7:15. No, we have we can join at 7:10. So let's take a 10-minute break, a quick break, and then we can continue. Okay.